this video, we're going to be talking about IC engines and specifically cylinder volume, clearance, bore, and stroke. In this video is part of a short video lecture series. And in the previous video, we introduced cylinder geometry, and we're going to continue discussing cylinder geometry. So if you want to go back to the previous video to get some more information on nomenclature and some equations that we're using, please go ahead and do so. If not, in this video, we'll continue that discussion. And what we're going to do is we're going to take what we defined last time and kind of move forward into some more equations and some more discussions of bore and stroke changes, as well as looking at what cylinder volume is and what cylinder clearance is. So just a reminder really quick to get started, VC, or the volume of clearance, is this area right here. And then in black, we have the volume of VD, which is our volume displaced. And we're going to write the equations down for both of these. So to start with, we're going to talk about VD, and we're going to talk about the displacement of the engine. And in order to calculate the displacement, we can do some geometrical analysis, and we can look at the system as a cylinder. And if we do so, we can say that VD is equal to pi over 4 times B squared, which is the area of the piston. Okay, B is essentially the diameter of the piston. So pi over 4 B squared is the diameter, the area of the piston based on the diameter. And then we're going to multiply that by S, which is the length of the stroke, or the length from top dead center to bottom dead center, which gives us our volume displaced. Now, this volume displaced is for one cylinder. And as such, the volume displaced of a cylinder is calculated as is. If we need to find the volume displaced for the whole engine, because an engine could have more than one cylinder, our VD would essentially be equal to pi over 4 B squared times S times the number of cylinders. So we would just multiply by the number of cylinders, and that would be for the whole engine. And this is important to note because sometimes when you're calculating volume displaced, you might forget that you need to multiply by the number of cylinders. So very important to not forget about that. If we want to look at for one cylinder, the other thing we could do is we could say that for one cylinder, VD is also equal to V at bottom dead center minus V at top dead center. So that means that we could look at the volume of the whole volume highlighted in red if we want from the bottom here. So anything above this line, this could be our V bottom dead center, and then we would do V bottom dead center minus V top dead center, which is the volume above this. So this can also be done. Okay. Another thing that's going to be useful for us in terms of understanding what's happening is just making sure we have a good sense of what units are and how we can convert units. So typically the volume is given in liters if we're using SI units, but this can be converted to 10 to the minus 3 meters cubed, which can be converted to 10 to the 3 centimeters cubed, and which can be converted to 61 cubic inches. Okay, so a lot of different ways to convert, and we can kind of look at the sizes in terms of conversion like this. Now, the next thing I want to do is kind of talk about, if we remember last time we talked about when bore is equal to stroke, we have something that's called a square engine. And if we start from a square engine, what I want to do is, if we start with a square engine and we decide to lower the bore and increase the stroke. So this could be something that we do. We lower the bore, increase the stroke, which would mean that we would essentially have an under square engine in this case. What I want to talk about is the positives and negatives of doing that. So kind of looking at what would be the positives and what would be the negatives of doing that. So let's look at the positives first. and the negatives. So one thing I want to do here in the video is, if you want to pause the video at this point and try to think of some positives and negatives, you can, and then you can resume the video to get to my list to look at what we have in terms of differences. So first positive is that we have more torque, okay? And this is because torque is directly related to the stroke length and to the length of your stroke, okay? So our torque is directly related to our stroke, and that means that if we have a longer stroke, we're going to be able to put a bigger torque through the rotational component that I'm going to highlight right here. So this rotational component, if we have a longer distance, there will be more force passed through it. Okay, and we'll look at with equations in further videos how that manifests itself in equation form. The other thing that can happen is our thermal efficiency would increase. Okay, and I'll draw it as the thermal efficiency goes up. And this is because if we have a shorter bore and we're looking at the engine from the top view, if our flame, for example, or our fire from our combustion is going from the inside out, if the bore is smaller, the combustion is going to take less time to get to the outside. So what we can say is the flame front travels a shorter distance. And right now we're not giving any in-depth explanations to what is happening, but down the line, once we have all the equations and all of the thoughts that go into looking at torque, work, power, and all the different metrics for performance, we're going to be able to understand why these are positives and how these are positives. Okay? One last positive is that there is also less surface area in your chamber. Okay, so less surface area in the clearance chamber at the top, and that allows us to have less heat losses. And less heat losses are a good thing in order to improve our combustion. Now, they're not necessarily a good thing always because you do want to cool your system if your system is running too hot. So this can be kind of a double-edged sword in the way that it is very, very positive on the one side of not keeping the heat in the engine to improve our thermal efficiency. However, we can lose some performance by the fact that we can't cool the engine enough and the engine might be running too hot. Okay, now let's look at some of the negatives. Okay, so some of the negatives are as follows. So for the negative side, we have more friction so slightly less efficient. So because of our increased stroke, this means that if we have an increased stroke, if we look at the equation for average piston speed, our average piston speed is equal to 2 stroke times n. Okay, 2 times stroke times the revolutions per second of our crank. And so if we increase the stroke, if stroke goes up, so I'll put if S goes up, that means that UP would also go up. If UP goes up, it means that it's going to be creating more friction along the walls. And what we can write is that there's going to be a higher skirt wear. And the skirt is essentially the material that is going to be placed along the line. So I'll draw it in red here. So it's basically this whole side here on the left and the right, that this skirt is going to be more more in demand, and we're going to have some higher wear in terms of the piston moving up and down. Okay, so one thing that happens too is that if we start increasing the stroke much and we reduce the bore, our UP will increase. Okay, so let's rewrite it really quick. So if bore goes down and stroke goes up, our UP is going to increase. But the problem is that we are limited by a maximum UP. There's a moment where if we go too fast and if we have too high of an average piston speed, we might start having problems with the wear, and we might start having problems with the piston wearing too much, and the force of the piston moving up and down is too much for the materials to handle. So something that we have to keep into account. Another issue is that the engine is less compact. Because of the fact that we've increased our stroke, that means our engine has to be taller. So we start having a less compact engine. And the last one is that we start having air losses. And what we mean by air losses is that in order to get the air in and out of the engine, we typically use valves. And if we reduce our bore, our valves are going to have to be smaller. So let's take an example of two different systems. So let's say that this is our B is equal to S system, and I'm going to over exaggerate it. Our bore is less than stroke system, just so that we clearly understand what's happening. Okay, so on the left side, we have a bore equals to stroke system where we can have two intake valves, for example, and two exhaust valves. And we can see that we have a lot of space to put these intake valves. So we can actually maximize the space for intake and exhaust. Whereas if we had to put them in a smaller bore now, our intake valves have to be smaller and our exhaust valves even smaller as well. So we see that we have less space to fit the biggest possible intake and exhaust valves. So typically when we're designing systems, we want our intake valves to take up the most space possible. And that's something that cannot be done if our bore is smaller. So that's one of the disadvantages of having a small bore. Okay, so we can see there's positives and negatives. And that means that we always have to counterbalance the positives and negatives. So we can't go too far one way and we can't go too far the other way, because we need to try and balance everything. That's why we always usually start with a square engine, because that offers kind of the best of both worlds. But we can veer away from that if we need to get more torque from our engine, or if we potentially need to prevent air losses, we could actually go with a bigger bore and a smaller stroke, for example. So you could do this exercise also by just flipping the script and making an over square engine where you would have a greater bore and a smaller stroke, and basically the negatives and positives would flip. Okay, one more thing I want to do in this video is I want to talk about clearance volume, and I want to talk about VC and how we would calculate VC. So VC, remember, is a clearance volume. We know that VC is also equal to V at top dead center. So it's our volume at top dead center. And we can also write that the volume at bottom dead center is equal to the volume of C plus the volume of D. Okay, so we're just defining what V bottom dead center and V top dead center is. And another term that we're going to use a lot in this video series, and a lot when you're talking about internal combustion engines in general, is compression ratio, or also called CR. Okay, the compression ratio is defined as the following. CR is equal to V at bottom dead center over V at top dead center. It essentially gives us the multiple by which we compress the fluid from bottom dead center to top dead center. So if we were to compress by or reduce the volume by 10 times, that would give us a compression ratio of 10, for example. So we can write this in terms of VC and VD. We get that this is VC plus VD over VC. And so we can use this to kind of figure out what our compression ratio for our engine is. Now, a typical compression ratio for an engine is usually around 8 to 16, but there's a lot of different variables and a lot of different ways in which you can calculate this number. Okay, so gives us a little bit of an insight into what compression ratio is. We also talked about bore and stroke and what changes to bore and stroke would actually do to our engine. And we also talked about what is the displacement of the engine and what is the displacement for one cylinder. So in the next video, we're going to start talking about work generation and power generation. We're going to start with work to define what work is. And then from work, we can derive what power is down the line. So I'll see you in the next video. Please consider subscribing to the channel if you want to. Thank you.